what's up? Yeah, in this video, I'm just gonna go through some simulations I made when I was doing my leaving cert. So let's get right into it. So you have some physics simulations. Start with dropping a mass at different heights. As you can drop a box here. Pretty cool. You can change the height and drop it again. If you really want to. Yeah. I think I pressed it twice, so you got 2 entries. But yeah, okay. I don't think Einstein said this though. Let's move on to the next one. This one's a bit cooler. So I guess just simulating where the object would be, the object or the image. I'm not actually sure which one is which. Set object is distance to 100 or minus 100. Minus 400. Yeah, presumably this is the image here. Or this is the object. The smaller one is the image. Yeah, okay. I got this long table you need to memorize for it. With your like diminished to virtual magnified images and all this stuff I've forgotten about. But it's a pretty cool project. Then the mark is just the line in the middle. And there's a bug where you can't bring it back to 0. I don't even know what's going on there. I think when the mark is null-ish in JavaScript, it just goes to the object. So, yeah. JavaScript messing me up 5 years later. Let's move on to the next simulation. Now this one doesn't... This one looks cool, but it doesn't correspond to anything in reality. Like, we'll go through this later, but basically this is meant to simulate the influence of a moving magnetic field on like some coils, but like magnetic fields don't look like this at all. So I guess you can change the field speed, more energy. You can change the number of coils. You can start with a plan. You can start with a field at a known distance. Or you can start with a known magnetic flux density at the core. And then you can execute the plan and look at the results. It's not like it stays static. I think I can lock it and then I can execute the plan and it will stay static. Yeah. But like it doesn't seem like you can't, or it doesn't seem like you can actually export any of this data. So you just have to have a good eye if you're doing it quickly. Okay. You can change the magnetic flux density. Magnetic field drop-off coefficient. Yes, this is totally how magnets work in the real world. I'm pretty sure when I set the coil to like a large number, it just gets extremely laggy. Maybe on older computers. Set it to 1000, see what happens. Prepare and execute. 10,000. Set coils. Prepare and execute. Keys. Modern technology. Yeah, I think that's basically it. Modify coil with a known area. Modify coil size with a known area. Alright, it's probably because I guess if you have an equation that gives you the area, you don't want to do the maths to convert that to the radius, so I let you do both. Which is cool, I guess. Yeah, then what does the reflection have? Some technical stuff. Virtual time, yeah, always use virtual time if you want actually simulations that are actually accurate. Don't use real clock time, because then if your program lags, your simulation is no longer accurate. And this is basically the complaint. So what did I write? I should probably change the magnet or remove it altogether, as it's quite disingenuous. The magnetic flux density around the point magnet does not drop off uniformly. There's dipole. You've seen the images. The magnetic field lines look like 2 ovals. Because of this, there's no simple formula that you can use to represent magnetic flux density as a function of distance. This is what Helmholtz coils are for, but they're not for point magnets. The magnet just represents an ethereal magnetic field, which is strong in the middle and weak at the sides. I've used linear drop-off as a function, as this makes it easier to match equations based off Faraday's law of electromagnetic induction. Some more simulation parameters would be cool, like an option to cause the magnetic field to move from side to side until unlocked, or an option to rotate the coil such that it would be at a different angle to the field. Great. We will not be doing any of this. So, pretty cool simulation. Chemistry, none of this actually works. This is cool though. This was a Rust project to repeat Thomson's experiment, but in simulation with a crappy bitmap font. I guess I did some Blender stuff, made the Blender model of the Helmholtz coil. The magnet is somewhere, or it's an electromagnet actually, so I guess the magnet is the coil. So what's the description here? J. Jane Thomson conducted an experiment to figure out the degree of charge of cathode rays. He constructed an apparatus consisting of a cathode, a hold is a crazy adjective, 2 parallel electrodes on a fluorescent screen in a vacuum tube. The purpose of the hold anode was to obtain a fine stream of cathode rays. The purpose of the 2 parallel electrodes was to deflect cathode rays. The purpose of the fluorescent screen was to visualize the angle of reflection or deflection of the cathode rays. He observed that the cathode rays were being deflected by the cathode and attracted to the anode. From this, he deduced that the cathode rays were composed of very small negatively charged particles. He used the name electron, which had been suggested half-decade earlier by an Irish chemist by the name of George Stoney. In another experiment, in addition to the influence of an electric field, Thomson put the electrons under the influence of a magnetic field. First, he deflected the electrons using the electrodes, and he brought them back to their original positions. Knowing the exact strength of the electric field and the strength of the magnetic field, he could then calculate the ratio between the charge on the electron to its mass. Can you? That's cold. Yeah, I don't actually have the source code to this anymore, and I don't know why it's green. I think the texture was broken. But yeah, long live this Rust project. And we have applied maths. Yeah, projectiles on an inclined plane. I actually showed this to my applied maths teacher. I was pretty impressed. You can change the angle of the plane. Click the simulate button. Does all the maths for you. Yeah. Can it change gravity if you are on the moon or something? You can change the angular offsets. Projectile. What was that? I guess just the angle it's shot out at, and you can change its starting velocity. Unlike the dropping mass one, oh no, this does scale the height of the animation, but I guess it doesn't scale the actual object itself, so it looks like it's just going slower. It would be cool if it changed the actual size of the sphere. Unknown variable. Yeah, I wanted to make an advanced calculator, but I just wrote this joke here. You use the space to do your calculations. I hear markers work great on screens. I was a comedian. Yeah. Then I also made this in Rust. But it looked, yeah, another bitmap font. I wanted to do like pulley simulation and inclined plane simulation. I think I only did inclined plane. Oh no, this isn't even inclined plane. This is an object sliding down an inclined plane, as opposed to an object being launched. Nice OpenGL project. But yeah, that's all. Thanks for watching.